Welcome to another podcast. In this episode, we're going to be taking a look at applying the methods we talked about in the previous video involving the Euler equation and the three cases to two different examples here I have of Euler equations. The first step on this for both of these problems is going to be finding the Euler equation. So let me go ahead and demonstrate that for both. The Euler equation is, remember, s squared plus, you take this constant and you subtract 1 from it, plus this constant here is an understood 1, so it's plus 1 equals 0. Making this look a little bit better, we have s squared plus 2s plus 1 equal to 0. So this is what this is defined as. This will factor perfectly into s plus 1 squared equal to 0. So we have two roots, s equal to -1. We have a repeated root case. Similarly, the Euler equation down here for the bottom problem is going to be s squared plus, here we have an understood 1, so it's going to be 1 minus 1s plus, here's another 1 equals 0. So this is s squared plus 1 equal to 0. So we have s squared plus 1 equal to 0, or s equal to plus or minus I for the roots there. So we have the complex case on the bottom problem. So if we are taking the top problem, then because this is my Euler roots, then y1 is nothing more than the absolute value of x to the -1. Remember, the root goes here. So this is the power of s equal to -1. And y2 is, remember, you multiply by the natural log of x. So this is absolute value of x to the -1 times the natural log. And remember, with the natural log, it's got to be the absolute value of x. Otherwise, we wouldn't be able to plug in x less than 0. And so my general solution is c1 plus c2 natural log of x times absolute value of x to the -1. All right, so there's 1 down. Now, if we had initial points, so if we had an initial condition, we would plug them in at this point. One thing I do want to point out is that y of 0 equal to b cannot be an initial condition. If b is non-zero. The reason being is only y of 0 equal to 0. This will have the solution y equal to 0. And that's just the trivial solution that you can see works. If I'm trying to solve any other value, say y of 0 equal to 2, then this is my general solution, and I would try to plug in x equal to 0. Well, the natural log is going to give me a problem. I don't know what natural log of 0 is. And so we have an issue at that point. There is a way around that issue, but it's a pretty lengthy way around it. We basically expand at a point near 0, and we look at the limit of the solution as x approaches 0. We're not going to talk about that in this course. In fact, I'm not going to talk about it in PDEs either if you go on to take PDEs. It might come up a little bit when we talk about the Bessel equation in PDEs, but it's sort of a hard thing to do to try to talk about solutions near initial condition points if you're talking about series solutions or Euler's equations or singular problems like these. But just keep this in the back of your mind that not every initial condition setup is going to work here. We've already encountered that this semester when we talked about the existence uniqueness theorem. So this is nothing new that some initial conditions work, some don't. But we just have to be very careful about any initial condition that involves y at 0 for this particular problem. All right, if we look at the bottom one is very similar because we're in the complex case. Then the real part is 0, and the imaginary part is 1. Remember, this is the same thing as 0 plus 1 times I, 0 minus 1 times I. So the real part is 0, the imaginary part is 1, which means that our fundamental set is the absolute value of x to the 0, or the real part, times the cosine of 1 times natural log of the absolute value of x. So this 1 right here is the imaginary part. This 0 right here is the real part of that root. Similarly for y2, you get the absolute value of x to the 0 times sine in this case. And when you put it all together, your general solution, absolute value of x to the 0 is 1, so I'm not going to include that, but your general solution is c1 cosine natural log of x plus c2 sine natural log of x. And once again, you have the same problem with the natural log here as you do in the equation above. So this is the simplest class of singular equations. It's also one of the most important classes of singular equations, as we'll see in the PDE's course. But for right now, I'm just giving you a solution technique to be able to handle these. So if you see an Euler equation, you'll know how to quickly look at the general solution for that. We're going to be looking at several of these here over the next week, but we're not going to get so far into it as to do some of the harder problems. So as long as you understand kind of what's going on with the Euler equations, you're going to be good for the most part for the singular equations we're going to look at in this course. We're going to expand that in the PDE's course if you go on to take that and look at some harder singular equations, specifically because they come up as solutions to partial differential equations. It turns out that when you solve a PDE, you have to solve an ODE, and oftentimes the ODE winds up being a singular point equation, and we need to know what to do with certain singular point equations when they arise. All right, thank you for watching.